Good afternoon. Hope you had a nice lunch. I'll be the chair of the session. We have three speakers. The first speaker is Milorad Milosevic, emerging superconducting electronics from diodes to neurons.
Thank you. Thank you, Tom, for the introduction. Allow me to thank the organizers for the invitation. It's a pleasure to be here. It's also an honor to participate in this celebratory event for the anniversary, the 30th anniversary of the Center for Solid-State Physics and New Materials. I come from a similar center at the University of Antwerp. I'm leading a computational materials modeling group for innovative technologies. I will connect to the previous speaker, Chedomir, to connect the fundamental science to, let's say, applications or prototypes of applications. And I'm leading a team of about 30 young researchers, talented researchers, trying to understand the origins of material properties, be it electronic, transport, optical, magnetic, superconducting, manipulate those properties at the nanoscale, tailor them at will, and then apply them as device functionalities at the micron scale. Okay? So multi-scale theoretical modeling is a common denominator, be it bulk materials, hybrid, heterostructures, two-dimensional materials, and so on and so forth. Okay? Also, the common denominator is high-performance computing, and we develop codes and algorithms for addressing all these challenging problems in material science, most of which are actually available to the scientific community. Now, today, I will talk about superconductivity, the reason being that that's where we had the most interaction with the center in Belgrade. And superconductivity for us is a long-standing topic for about 20 years, but we started from fluxonics and devices based on vortex matter, vortices, and understanding their behavior in applied magnetic field and applied current. Extended that to three-dimensional architectures, type 1 superconductors, most elemental superconductors being type 1, where the challenge is to correctly calculate and address the long-range magnetic fields coming out of the superconductor. Then Josephson physics, the Josephson junctions and Josephson phenomena between the superconductors using various models. Going to the nanoscale below the characteristic length scales of superconductivity, so when we confine electrons and Cooper pairs at truly at the nanoscale, what is the emergent phenomena there? Unconventional being unconventional hybrids, not unconventional superconductivity. Superconductor ferromagnet hybrids, or as antagonistic phenomena in solid-state physics, or graphene-based and 2D materials-based junctions. Semiconductor superconductor hybrids that are relevant to Majorana physics and, for example, the Microsoft path chosen to qubits. And finally, atomistic simulations, meaning origins of superconductivity at the atomistic scale. So electron-phonon coupling, Eliasberg theory, and connecting that to different scales, and also understanding how superconductivity changes when we take the material and thin it to the thinnest limit. Okay? And this you will hear more about in the talks by my colleagues, Šoškić and Bekart, a bit later on this conference. I will focus on superconducting electronics today. Just chose a topic that should be, let's say, interesting and entertaining to most of you. Why superconducting electronics is interesting? Well, for one, is low dissipation. That's kind of clear from the superconducting properties. But it's also low noise, low loss, extremely nonlinear, high resolution, very high sensitivity type of electronics. Okay? What is the drawback? Is the cooling, obviously, that one has to do to reach the superconducting state. Okay? But everything else is a plus. So one commercial device that is widely available is a superconducting single photon detector. It's nothing else but a superconducting wire that is meandering and covering as much space as possible. This is about 10 micron by 10 micron. And then if we measure the current voltage characteristics, we will be here in the superconducting state below the critical current, 0 voltage, 0 resistance. And then we will have if we operate our nanowire just here, just below the critical current, when the photon impacts at any part of this nanowire, it will locally suppress superconductivity, and we will have some resistance. Okay? This is what we call a resistive state, right here. And if you keep pushing the current up, then you will reach the normal state. Okay? But we are going to be here, we are going to have an onset of a voltage pulse, and if we then shunt our this nanowire single photon detector with another resistor, with a resistance lower than the resistance of the resistive state, the current will go that way, superconductivity will recover, and our detector will be ready to detect the next incoming photon. Okay? So that's the basic idea. And I show this because I will need it a little bit later for the other devices that I will be discussing. Okay, so next to this, that is fully commercially available, there are also squid detectors, magnetoencephalography. Any better equipped hospital will have, this scan of the magnetic field of your brain based on squids and Josephson junctions. Josephson junctions are the base of a large set of electronics that's readily available, like this random access memory from the Lincoln Lab at MIT with a record-breaking 4 million Josephson junctions per square centimeter that is actually based on 3D electronics, on multi-layer niobium structures. Okay, and Josephson junctions are realized here by proximity of the two layers. Okay? Or superconducting diodes that are up and coming. I will not spend too much time on that because I'm sure that Mojan Ali will discuss that a few days from now. But the idea here is that you break the inversion symmetry of your superconductor one way or another, so that for one polarity of the applied current you have superconducting state, but for the opposite polarity of the applied current you have normal state resistance. So in one case you have no resistance, in the other case you have maximal normal state resistance. Okay? So these are things that are very well developed. Okay. Also, why is this interesting? Because of the second quantum revolution, qubits, all qubits that we hear about these days by big companies, IBM, Microsoft, Google, are based on superconductors one way or another. Why is that? Because we are able to fabricate superconductors with high chip density and control or read out both input and output in more ways than one. Okay? So these are not best qubits in terms of coherence or other properties, but are best for technology. Okay? That's why there is heavy investment in superconducting electronics as well. Okay. So last but not least, I want to draw your attention to the rise of energy demand. And this you very well know, but just this computing, data processing, machine learning, and artificial intelligence, ChatGPT, the clusters and the servers of Google and Microsoft are eating up enormous amounts of energy, and actually individually they consume more energy than individually half of the countries in the world, more than 100 countries. Okay? Serbia is a bit higher here on the list, but nevertheless consumes less annually than Google and Microsoft together. Okay? So there is a need for superconducting electronics. It's more appealing than ever. The cost of cooling is nothing compared to the gain for these computations at the exascale. Superconducting single photon detectors we have, superconducting diodes we understand. I will not spend time, but I will talk a bit about superconducting field effect transistors and artificial neural networks as the next step. Okay? Good. So I'm a theorist and computational scientist, so the theory that we are using for this task is Ginzburg-Landau theory, time-dependent Ginzburg-Landau theory. The first Ginzburg-Landau, time-dependent Ginzburg-Landau equation being this one, which we are solving for delta, which is the superconducting order parameter, gives us density of carriers of superconductivity, right, locally. It is coupled to the second equation for the magnetic field emanating from the superconductor. This is a magnetic vector potential that enters right here. Then we have the current conservation law, or the electrostatic potential, Poisson type of equation, which we solve for this electrostatic potential phi, and it enters both in this equation and in this equation. And finally, anytime when you have a resistive state in a superconductor, you have heating, inevitably, Joule heating. So you have to solve the equation of thermal balance, the heat balance equation, that depends on heat capacity, how fast the temperature is changing, heat conductivity, how far-ranging is that change, and coupling to the, let's say, the bath, okay, depending on the normal current in the superconductor. All right? These four equations have to be solved, generally speaking, self-consistently. Okay, so it's a formidable task. In some cases, we can eliminate some of them, but generally speaking, you have to solve all. These temperature dependencies here, Ginzburg-Landau theory is derived very close to the critical temperature. Strictly speaking, is valid only at the critical temperature, but in comparison to experiment and following some empirical expressions proposed by Ginzburg many years ago, this actually is proven to work at very low temperatures, far from TC. Okay? Good. So in these simulations, we can take arbitrary geometry of the circuit. We can place leads. This is a Corbino geometry, so I'm putting current in here, taking current out there, and I'm monitoring how vortices are moving. So you see that that works and that the velocity, vortex velocity changes radially as the current changes radially. We can model single photon detectors. Here, for example, at Karlsruhe Institute of Technology, they were wondering about the effect of edge quality of nanowires on the performance on these single photon detectors. So we did that. And we are able to do that at large scale. This is a commercial scale of the single quantum company in Delft, 8 micron by 8 micron single photon meandering nanowire that I just showed. So we can do that with a resolution of 1 nanometer, let's say, okay, spatial resolution. So it's all working fine now. We can also put spatially dependent parameters, be it inelastic scattering, be it mean free path, be it heat balance equation, the normal state conductivity, thickness, all of that can be done with, let's say, 1 nanometer resolution. Okay? And this was proven in these previous papers. So we take from experiment directly the shape and all the properties that experiment can give us. For example, here was TC that was varying from one place to another, mean free path that was varying from one path to another, and we put that in the simulation without any fitting parameters, okay? And seems to work. Okay, so now I'm coming to the base of all the technology that I'm going to talk about. It's a plain superconducting stripe. It's as simple as it can be. So we have a superconducting nanowire. This is a 4-probe measurement, typical. Here the current is applied, and here the voltage is measured. What do you get then? You get exactly a type of current voltage characteristic like here, superconducting state up to some critical current, resistive state, and then normal state. This is ohmic resistance right here, okay? So what is this resistive state? Well, there are two possibilities. There is a so-called phase slip, which means that there will be a thin region about coherence length wide of suppressed superconductivity, where the phase of the order parameter from one side to the other will change by 2 pi. That's why it's called a phase slip. Another possibility is the hotspot state. So it's again similar thing, similar dynamics, but this normal state is going to heat up the superconductor, and we will have a larger region where superconductivity is destroyed. From resistivity alone, you cannot tell which one it is, but from the dependence of resistivity on temperature, you can experimentally determine which one you have. Okay? But these are the resistive states that I will be talking about in the rest of my talk. And that's all. Okay. So now, field effect transistors. Is it possible? It's a base of electronics, right? Can we have a superconducting field effect transistor with minimal dissipation? In order to have that, we need to have effect of a gate on a resistive state of a metallic superconductor. Okay? As a physicist, you imagine this is not possible due to screening, right? So let's see. A couple of years ago, there was an experiment, superconducting wire, aluminum, titanium, and then gated from the side. Okay? This was about a couple of hundreds nanometers wide, so you see it here, 300 nanometers wide, and the gating was applied from the side. Okay? Intuition tells us that nothing should change in the superconductor. However, they measured IV characteristics, and they see that IV characteristics depends on the applied gate voltage, which is right here. So there is a strong effect of a gate on a superconductor, in fact. It is temperature dependent, so this is the critical current, the onset of resistance, as a function of gate voltage, and you see that it is temperature dependent, and you see that there is a flat region up to which there is no effect of the gate, and then beyond some critical gate voltage, there is suppression of the critical current. Okay. It's a bipolar effect, so it's perfectly symmetric with respect to positive and negative gating. But there is a problem. The problem is that these gate voltages are very large, the order of tens of volts. Why is that a problem? Because in order to integrate this with existing CMOS electronics, we have to get these gate voltages below 5 volt. But more importantly, we need to be able to connect transistors in the series For synchronization, we need to be able to use the output voltage of one transistor as the gate voltage of the other. Okay? That is far away from what we need. So because the input voltage is, let's say, 30, 40 volt, the output voltage is on millivolt scale. Okay? So we are far off. So we thought this side gate system is not the optimal choice, especially not if superconductor is thin. So we said we should look at out-of-plane top gate system, okay, to expose the entire stripe to the gate voltage, optimize the thickness of the oxide, this will turn out to be very important, and also optimize the width of the nanowire that is used here. Okay? So when you have an idea like that, you talk to an experimentalist, and preferably you need an experimentalist with deep pockets. Some people go to China, we went to Saudi Arabia, and we have so this is a maybe not so well-known university, King Fahd University of Petroleum and Mineral, but actually standing very high in the QS international ranking. They have a very nice pulsed current system and transport measurement, and this is the system that we designed, niobium titanium superconducting stripe of width 3, 5, or 10 microns, so significantly larger than the previous one. Thin, 50 nanometers thin, so that we have uniform gating across. Ultra-thin oxide layer, 25 nanometers, and then gate coming all around. So this is the so-called FinFET design architecture. Okay, so we are sure that we have gating from all sides of the stripe. Okay, so this is the result. We have, as a function of temperature, the strong effect of gating on the critical current, and we have that the reduction of the work operating gate voltage at below volt. It used to be tens of volts. Okay. Then we have asymmetry. It's no longer symmetric, but it's asymmetric. I don't know if it's very clear, but it's not bipolar. Okay. Then the onset, this critical value for the onset of the effect is depending on temperature. And this critical VG is depending on temperature. So these are all features that are different from the previous side gated system. This is important because it helps us identify the mechanism for the gate effect. The previous was never understood. It was just called the field effect, whatever it may be. Okay? That we don't have direct field effect because otherwise we don't have a symmetry between different polarities of the field. Okay? So we eliminated that. The direct emission of high charge, of high density carriers from the gate directly to the superconductor is not possible because our oxide thickness is still sufficiently thick. Phase fluctuations probably play a role, but not at temperatures, at all temperatures that we considered. So finally, we realized that it's only the phonon heating in the oxide that is important for this effect. And the asymmetry is due to the fact, are we injecting electrons from the gate to the superconductor or from the superconductor to the gate? In one case, we get phonon heating at the top of the oxide, in the other at the bottom, and that creates the asymmetry from the point of view of the superconductor. Okay? So with that in mind, we go to theory, and Leonardo came up from microscopic derivation with the energy term, sorry, the temperature dependence, temperature change term in the Ginzburg-Landau equation that is of this shape that depends on the gate voltage and has temperature independent factor B here that can be used for all stripes regardless of their width. And then temperature dependent term here that determines the effective heating in the superconductor. Okay? And using same A and B for all of the temperatures here, we get nearly perfect description of the experiment. Okay? And using the whole theory simulations that I've just shown. So this is really a major step forward. Why? Because in addition to it working, we now can connect the two transistors in a series because our output voltage is, let's say, up to 0.4 volts in this case. This is experiment, this is theory, and the input voltage is on the same scale. Okay? And can be, of course, further tuned if we really want to do that. Okay? So I think, field effect transistors, superconducting ones are nearly there. Good. Now, the second example that I want to discuss in the short time that I have are the artificial neurons. Okay? So we want to mimic the performance of a neuron, biological neuron, by hardware. And this is something that has been done by CMOS technology. There are commercial realizations of it, Neurogrid, True North, Loihi, and this is the energy consumption per spike. So if you will remember, each neuron generates a spike as a response to the excitation. And here I will show the same superconducting stripe that I just used there for gating. I will use it for a different purpose as an artificial superconducting neuron. And the energy consumption will be the lowest of all the energy consumptions of all the products on the market. Now, so this is the biological neuron. You will know that you have excitation and repolarization effects, so basically a voltage spike by opening sodium and potassium channels in the cell. What we are proposing now is to look at the resistive state of a superconducting stripe. Okay? So this is my superconducting stripe, and if we apply current and as a function of time now measure the response, we will get a hotspot for sufficiently large current that I'm in the resistive state. Okay? And if I then shunt this nanowire, then I will get reduction, and then again the rise of the peak and reduction, and so on and so forth. Okay? So this time of the rise and fall is determined by the electronics, by the shunt resistor and the inductance of my circuit. Okay? And this is the physics of a superconducting stripe in applied current. So quite simple, I think you will agree. Good. So what is the analogy to superconducting to regular neurons? First of all, you need to have a threshold response. The neuron only fires if the excitation exceeds certain value. So we have that. That's the current exceeding the critical current. Okay? Refractory period is a critical time below which two signals cannot be distinguished. So if you apply a pulse of current and another pulse of current, there is a critical time in between that your superconducting neuron can react to it and give you the voltage spike, similarly to the neuron. Then we have the class 1 or 2 behavior, meaning if I increase the excitation, will the frequency of these spikes increase, yes or no? Okay? In superconductors, it will. So it's a type 1 type of neuron. So the frequency will increase. Okay. So we did experimentally the voltage output. This is shown here as a function of applied current. We are just above the critical current, and we are increasing the applied current. Okay? And what you see is that in a fixed time of 500, actually the pulse is 400 nanoseconds, the current pulse, you see one spike, 2, 3, 4, and number of spikes increasing. Okay? So it's on the similar time scale. It will depend on depend on type of neuron because there are many different. No, I didn't look at that. Yeah, but I suppose it can be engineered. So basically the frequency, if you see it here, increases with applied current and increases by a factor of 3, 4, maybe an order of magnitude. Okay? As a function of temperature, we can have a dependence, and characteristic times for this rise and fall, as I said, can be controlled by the electronics. Okay? Good. So theoretically, we did the simulations and we get the exact same thing. The hotspot generated, then recovered, generated, recovered, and as we increase the current, we have exactly the same behavior with a shunt resistance. There is a shunt resistor coupled to the nanowire of a particular value. This is important. Okay? Good. So the problem is if we try to crank up this frequency, at some point we have a problem. You will see here, so I'm doing, this is the same measurement, just I'm increasing the current further. Here I had fully occupied 400 nanoseconds of spikes, but then I start losing them, and this level of resistance, this voltage, is higher than this one here. You don't see it maybe very clearly. This is us killing the neuron, or the artificial neuron, okay? What happens is that instead of bouncing from the hotspot to the superconducting state, hotspot to the superconducting state, the system prefers to go into the phase slip state and remains permanently in the phase slip state. Okay? So this is what it looks like in simulations, the voltage versus time, and this is what it looks like. So it goes up and down, hotspot, hotspot, and then finally just remains in this phase slip state all the time. Okay? And that's not what we want. for the neuron. So we have to stay within a range of currents where we can fully control this spike behavior. This range of currents and the frequencies of spikes will depend on the shunt resistor as well as the properties of the superconducting stripe. Okay, so now we decided let's make a neural network. Okay, I'll speed it up, I have only 2 slides. But basically we use same stripe, but shunted with different resistors. Okay? And if I take the same stripe that I just showed you with 3 different resistors, okay, this is in some theoretical units, but let's say it's about ohm, 2 ohm, 3 ohm, okay? Then we get different frequency of spikes in the same time period for the same applied current, okay? So now what I do, I will skip this, I take an image. In this case, it was a simple 3x3 image where image of a number 4. Here we should have, let's say, value 1. Here we should have 0. And this 1 is the value just above the critical current, as 0 is the value below the critical current, of applied current. I apply a sequence of current values, 1, 2, 3, 4, 5, 6, 7, 8, 9, all of them in a sequence to each of the neurons. Okay? And I get a sequence of voltage versus time signals of the 3 neurons in this case. This example is for 3 neurons. Then we take a software, and based on the cross-entropy loss function method, we just optimize the weights of the 3 neurons such that this image is correctly recognized. Okay? And we do that for thousands of images where we allow this to be 1, 0.9, 0.8, 0.7, and this 0, 0.1, 0.2, 0.3 to account for error, for the grayscale in the image. Okay? So then after we do the training, this is the result. The idea is that when we apply, here was number 4, in theory and in experiment, when we send through 1,000 images of number 4 with different, as I said, grayscale here, that the solution, the output signal number 4 should always be the highest one. Okay? Understand that not all of them are going to be correct, but the highest frequency one is going to be the correct one. And actually, this works really nearly ideal. Okay? So I see the chair rising. So I hope to have convinced you that we already have single photon detectors fully functional. Diodes are almost there. Field effect transistor. I have a simple proposal, artificial neural network, simple proposal that works. There is a whole topic that I hope to share with you soon about two-dimensional van der Waals superconducting electronics. And this is really pushed forward by fantastic advances, again, in China, on wafer scale grown superconducting 2D materials that can be set up in these Josephson junction architectures. And there's more to come in quantum communication, cryptography, and so on. So allow me to thank my collaborators on this work one more time, and thank you all for attention. Sorry. Thank you. So I'm not sure what you mean, but our input is not DC. Well, it's a pulsed current with a length of, let's say, 400 nanoseconds in this case. So it's in principle time-dependent input and time-dependent output. Yes. Okay. Yeah. Obviously, we are not that far in this design, but I will think about that. Yeah, thank you.
I have a quick question. Back to the gate, the 3D gate. So how is it that the voltage launches these phonons into the electron? What's the mechanism behind it?
So it's the injection of electrons, in fact, and the carriers from one side or the other that interact with phonons and lead to phonon heating in the oxide itself. Exactly. exactly. So we actually, okay, there's a lot of trial and error behind this concept. We tried different materials, different thickness, so I present you just the one that really works well, but I mean, you're correct. So in the case of transistor, we deliberately made them wide, so it's a microns wide. And the reason was to maximize the output voltage, because I wanted voltage to be comparable to the input voltage. So it was 3, 5, 10 microns wide. But for the neuron, it doesn't really matter. Yeah. Yes. But we are far. Yeah. Well, we are far from that one. Far from it. Yeah.
Well, in low DC superconductors, your carrier density is something like 1022, 1023. Your transfer string length is 2 angstroms. Therefore, electric field just cannot penetrate down. Is it
Correct.
possible that, I didn't think of this before, but is it possible that with the top gate, you actually could have something like a hot spot where your top layer gets hot and then it heats, electric field goes deeper and
So we interpreted it. That's exactly what I was saying, but just the heating was in the oxide between the gate and the superconductor. But it could be, yes, then it heats. Exactly. That was the interpretation.
When you're training these networks, what is the training parameter with the weights between the mirrors?
So as always, it's the weight of combination of the three. But so in this specific entropy loss function, every time when the result is correct, the weight is increased, let's say, is rewarded positively and opposite.
But what is the weight?
It's a multiplication. No, resistances are fixed. So this is done. Just the signals. Yes, exactly. Yes, the resistances are fixed.
Let's thank the speaker again.
Thank you.